So hi everyone, my name is Pengbo Yan, and I'm a second-year PhD student at the University of Melbourne. Today I'm going to talk about my PhD research plan, proving obliviousness of probabilistic algorithm with formal verification. My supervisors are Toby Murray, Tuan Pan, and Rob Sazen. So the security of a system relies on the security of all its parts. To explain which parts my research focus on, we'll consider in the context of the web server, whose job is to serve queries to a customer database while protecting the privacy of customers whose data is in there. And there are many components in the system, such as the server, including its CPU, memory, and the software running on it, and the internet, the browser, and maybe some data published to some users. So the attackers may try to do some things to get some sensitive information or make the system unavailable for each component or between the channel between each component. And correspondingly, the defender also has some security standard or the techniques to defend against those attacks. And my research focus on the obliviousness, which is a security standard, which will defending against the side channel attack between the channel of the memory and CPU. And then I will explain this kind of attack. So suppose there is a cloud server running many people's programs in a physical CPU in turn. So for example, including the victim's program and the attacker's program. In this case, the attacker's programs may evaluate how long time it takes to access a memory location, and then infer whether this location is loaded into the CPU's cache by the victim's programs. So there are many research and tools for doing so. In some cases, the attacker's programs can even know the complete sequence of the location read and written by the victim's programs in some case. And we will call this sequence of the location read or written by the victim programs as the memory access pattern. And this memory access pattern may be known by the attacker. So here is a program how this memory example, how this memory access pattern leak information. So suppose there is a table including some sensitive information, for example, some people's ages and salary. And suppose our collaborator want to query them for their research. And as a result, we only allow some limited queries. For example, we only allow the query the median or the average of each row of data. We don't allow the query of the personal information. Maybe we will add some sometimes we may want to also add some differential privacy mechanism to enforce the privacy. But the memory access pattern with some algorithm sometimes may still leak the information. So for example, if we allow the median, this function, and suppose our implementation is that we use the selection sorting, and then we return the middle number of the sorted array to get the median number of an row. Then suppose the memory access pattern is known by attacker. Then what we will do by this implementation is that we will try to sort the row of ages. For example, we swap this 60 and 30 as a first step, and then we swap the 60 and 50 as a second step. So if this memory access pattern is leaked, then the original order of the elements in that array is also leaked to the attacker, which is some additional information that we don't want to review. So in this case, it's an example about how memory access pattern leaks information. If the attacker run multiple queries this median queries on multiple rows, then the attacker may infer and deduce more information. So there is a definition called obliviousness to defending against this kind of attack. So the previous example, leak information via the memory access pattern, because the sequence of the origin data decides the memory access pattern directly. And an oblivious algorithm is the one that always have the same memory access pattern, whatever, regardless of the sensitive data is. So that means the memory access pattern is independent from the sensitive data in an obliviousness algorithm, so that it will not be leaked by the memory access pattern. And if we want to rewrite the previous program to a safer version, we can change the selection sorting into another oblivious sorting algorithm. Also, there is a probabilistic version of definition of obliviousness for the better performance. So for example, the Malvern shuffle is an oblivious shuffling algorithm. It is probabilistic and its complexity is O root n, whereas its fastest deterministic version, its complexity is O log n times root n, which is slower. So the previous deterministic version said that the memory access pattern must be same over all the possible sensitive data. But the probabilistic version said that, okay, the memory access pattern may be different in some case over different sensitive data, but their distribution must be same. So it's kind of random, but regardless of the sensitive data, the distribution of those random access pattern must be same. In this case, the memory access pattern is still independent from the sensitive data and will not lead any information of the sensitive data. So given those definitions, we want some techniques to verify, to prove our programs satisfy the definition of the obliviousness. And the formal verification is such a tool to prove a program satisfying some properties. Different formal verification logics there are many different formal verification logics for proving different kind of properties. So for example, there are Hall logics for proving the variable's value, and separation logics for proving memory safety, and the relational logics for proving the information flow securities. And there are some existing works for proving deterministic obliviousness. Those works are quite mature. It's well studied. But the existing work for verifying probabilistic obliviousness are not mature. One of the reasons is that the probabilistic properties are relatively difficult to prove. And my aim is to develop formal verification logics for verifying probabilistic oblivious algorithm. So there are at least two main aspects of challenges. The first aspect is that existing work only supports a small subset of probabilistic language. And the second main aspect is that some probabilistic oblivious algorithms are imperfect, which is hard to deal with. So there are also 5 small points of the challenge, and I will introduce the first 3 of them, which is the first main thread of challenge in the next example. So here is an oblivious sampling algorithm, which takes an input D, which is a database including n pieces of data, and it will return k list with m random pieces of data in each list, which is independently randomly sampled from the database D. So this algorithm has 2 parts. The part 1 will randomize this SWO, which will determine the allocation of those output lists, and then store the detailed allocation in S with these flavor loops. So the first part just going to construct this long list S. This long list S, one of the example is in red color. So it may contains is a list of tuple, and each tuple contains two elements. The first element is some encrypted data, which will be returned finally. And the second element is the index of the list, which the data should be in finally. So for example, if this S is as the red colors shown, then that means there are 4 encrypted data, sampled data in the list, and 2 of them should be in the S1 finally, and the other 2 should be in the S2 finally. So the first part of this algorithm is has the deterministic memory access pattern, but this S is a truly random distribution, but the memory access pattern of the first part is deterministic. And the second part will shuffle S and then allocate all the results into those output list. The second part, memory access pattern, is truly uniformly distributed because we are going to shuffle S, and this S will determine this S determine and only determine the memory access pattern of part 2. So there are some existing works, some symbolic execution and the type system or the programming logics, which can be used to prove some of this oblivious algorithm, but none of this can be used to prove the previous one. So for example, the first one is Obliviousness, and the third one, this lambda OADT plus, cannot be used because it only works on the deterministic definition of the obliviousness. And the second one, this lambda oblivious, also cannot be used because it's based on a functional language. It's not very suitable, and more importantly, it do not support the asynchronous branches on the sensitive data. And moreover, none of them support the dynamic random choice. So which means by this, if we look at the code, line 15, there is a shuffle. We are going to shuffle this S, where this shuffle is a list. We just want to shuffle this whole list, but this list S is a truly random distribution at here. It's not a static value. So all of this program language or symbolic execution or type system just support the static random choice. That means we need to figure out what is the random choice based on before the program begin. But sometimes we need some dynamic random choice, and they do not support those. So then the last one, this PSL, should be the still cannot prove or verify the previous algorithm, but I think it's suitable to be the start point because I think its structure is suitable for this M, and I have some ideas to extend PSL to make it available to prove to verify the previous algorithm. Then I will introduce those ideas. So the previous slide showed the algorithm before has some features that make PSL cannot verify that. For example, the challenge 1, there is a random loop. The random loop here means the number of iteration of this loop is random. So the PSL only supports some loop which has the deterministic iteration number. But sometimes the loop just has some random probabilistic iteration numbers, and PSL do not support that. And secondly, there are some if statements whose if condition is not independent with its if body. PSL only supports some if condition, this if statement whose condition is independent with their if body. And PSL has such restriction because it always consider the whole distribution everywhere. of the program. So it always considers the distribution. It's always saying this program is a really probabilistic program, and it wants to reason about the distribution everywhere. But in this case, so the part one of these algorithms actually only has the deterministic memory access pattern. And actually, because we also need some information to verify the second part, we also need some additional information. But those information is not about distribution. Those essential information is always true in every possibilities. So my solution is going to say, in sometimes we can reason about a part of a program as a no-deterministic program. We just, in this case, we just say the part one of this algorithm as a no-deterministic program. In this case, we can have some more powerful rules, although we cannot do that in the part two. So the strategy is that we think the part one as a no-deterministic program, but we say the part two is a truly probabilistic program to solve that. In this case, we can have some more powerful rule to overcome the limitation of PSL. And for the second part, there is also some challenge, said that there is a dynamic random choice, which I have explained before. So PSL do not have this, do not support this dynamic random choice. And my solution is going to extend the PSL semantic to let it support that, and add some new sampling rules to get some essential information. So in this case, we say that this S is truly random distributed. The first part of that is very random, but we know some certain information of the second elements in this S. So namely, we know that there are 2 of 1 and 2 of 2 in the second elements in this S. So in this case, we want some new sampling rules, which can take some partial information from the distribution of this S after this shuffle. So we want to know that after this shuffle, the second elements satisfy some distribution, but we don't care about the first elements. That's what we want, to get rules which can get some partial information after a dynamic random choice. So far, I have now is the 4th year of my second year. So in the the 4th month of my second year. Sorry about that. So in the first year, I explored the background and I extended the PSL for addressing challenge 1 and challenge 2, which is about the loop and if statements. And currently, I'm tackling challenge 3 about the random choice, which is talked about in the last slide. I'm also formalizing those results in Isabel. It's still ongoing, not finished. And I plan to finish it in the next few months. After that, I believe I can verify the oblivious sampling algorithm, which I introduced before. Then the future plan, including to tackle challenge 4 and 5, to verify those more complicated oblivious algorithm, which is imperfect. And in the third year of my PhD, I plan to develop symbolic execution and automatic tools, which will make the previous result more easy to use. And finally, I also plan to explore more probabilistic security standards to apply, such as the differentially private obliviousness, which is some new definition of the obliviousness. Okay, that's all of the content I'm going to introduce. Any question or suggestion of my research? Yeah.
So can you show the algorithm?
Yeah.
So what is the, you say you want to randomize SW, or what is the more formally the specification that you want to verify for this?
Oh yeah, that's SWO's specification is a little bit complicated. It satisfies some features, but generally it's a randomization from a set which only decided by this n and m, these two integer. I'm not sure whether it answers your question. So the
what about the spec for the algorithm itself, like the overall specification that you want to prove for the whole algorithm, like ignoring SWO, right? Like what is the high level spec?
Yeah, so this algorithm, like let's say it has two parts. One part of that is its correctness. It's going to say the returned list is some truly randomly distributed sampled. And the other feature is the security feature. The security feature is talk about this program's memory access pattern do not leak any information of its returned value.
I think I was asking more generally, are you trying to prove that this is a random permutation of the values?
No, I'm not going to prove the correctness of this program. I'm going to prove the security feature of this program, which means the memory access pattern of this program do not leak the information of the SWO like that. So because we are talking about the obliviousness, the definition of obliviousness, not sure.
I'll ask you offline, but can I ask something else? The PSL, you said it cannot prove loops that have a random runtime.
Yeah.
Why not? And how did you fix it?
Because the PSL, if you look at the PSL pair, you will find that they restrict the loops condition must only include deterministic variable. So PSL distinguish deterministic variable and probabilistic variable. So the deterministic variable can only store some deterministic value. It cannot store some random value. And the PSL's loop condition can only contains deterministic variable. That just means its semantic just do not support random variable in the loop condition. So the loop cannot be probabilistic. And I want to extend the PSL semantic to allow it write the random variable in the loop condition.
Oh, you didn't do that
yet? Yeah, I have do that.
Ah.
But not published yet. It's still ongoing. I think I will try to submit the paper later after I finish the more plan, like after I finish the tackling Chinese 3 and to verify the oblivious simply algorithm after that. Yeah.
Intuitively, how like was it much more ever since challenges 1 and 2, was it much more complicated, the logic that you have at the moment, or like yeah, how does it differ from the original PSL?
I think it's for the challenge 1 and 2, it's a little bit like to add another mode or add another strategy into PSL. So PSL's strategy is always considering probabilistic program and always consider the whole distribution. But we just want to add some new strategy into PSL. That strategy is not very new, so it's just some normal or standard verification strategy when we reason about a non-deterministic program. But in this case, we just want to sort of combining the strategy of reasoning about non-deterministic program and reasoning about probabilistic program. Sometimes there are some benefits. So we just want to add those strategy to PSL. It's not very complicated. I think the most complicated challenge is how to define the random loop, how to deal with the termination definition or the assumption of that extension. There are some challenge about that, but the strategy itself is well explored and not very challenging. Maybe the second part has some challenge, I think, about
the insights of your work is that so far is that when reasoning about a probabilistic program, it can often help to instead reason about an abstraction of that program where you replace probabilistic choices essentially by non-deterministic choices, right? And then reason about that program instead. You said that that's useful because for a lot of the reasoning, you don't need to actually talk about the actual distributions. You just talk about the values that might arise instead, right? Which you can do with a non-deterministic abstraction if you don't care about the probability that different outcomes occur with. Do you reckon? I don't know the answer to this. Do you reckon that that strategy could be useful for other logics for reasoning about probabilistic programs, or is it the case that it's a strategy that is especially useful for PSL because of how PSL is structured?
Yeah, I have some idea about also add this strategy to some other logics, but it's still not a very mature idea. But I believe it is useful in some other probabilistic logic. But I haven't do any formal research on that.
Cool. Any more questions, comments? Questions?
So you were talking about like having a logic for reasoning about obliviousness, but then you talked about just having a logic for reasoning about probabilities. So is it actually like, is the logic that you're developing particularly for proving things about obliviousness, or just or proving any probabilistic properties in programs?
Yeah, I think the original motivation is about obliviousness, but probably the final logic outcome it will be a little bit more general. It's possible to look at some others. I also try to look at some others example, like the those example in PSL. There are some others aspects other than oblivious algorithm. I think it's also possible to do that as well.
Great. So we actually finished pretty much on time. So thanks again, Penguin.